The discovery of 3I/Atlas has rapidly become one of the most intriguing astronomical events of the decade, and in the past 2 months, the world's most powerful telescopes have directed their attention toward it, attempting to decipher its mysterious nature. Telescopes such as Hubble, JWST, SphereX, and TESS have all played a vital role in gathering data. Yet instead of revealing a predictable and familiar profile, the interstellar comet has consistently defied expectations. Every new piece of information seems to challenge established knowledge about comet formation and behavior. From its strange chemical composition to its unusual activity patterns and uncertain dimensions, 3I/Atlas has transformed what could have been a straightforward scientific observation into a complex frontier of interstellar research, pushing astronomers to reconsider many long-held assumptions. 3I/Atlas was first spotted on July 1, 2025, by the Atlas Survey Telescope in Chile, a facility designed specifically to detect fast-moving or potentially hazardous objects in the sky. Almost immediately, astronomers realized that this newly detected object was not simply another comet originating from the distant edges of our own solar system. Its hyperbolic trajectory revealed that it was not gravitationally bound to the Sun at all. Instead, it was on a one-way path, entering from deep interstellar space and moving through our system only briefly before continuing on its journey. This placed 3I/Atlas in an extremely rare category of celestial visitors, making it only the third confirmed interstellar object ever observed. It follows the historic detection of 1I/Oumuamua in 2017 and the comet 2I/Borisov in 2019, both of which sparked massive scientific interest for their alien origins. However, while Oumuamua and Borisov each had their own sets of unique properties and mysteries, 3I/Atlas seems to combine unusual characteristics from both while introducing entirely new ones. Immediately after its interstellar origin was confirmed, major observatories around the world coordinated their efforts to study the object. The James Webb Space Telescope, known for its extraordinary infrared sensitivity, was among the first to target 3I/Atlas. On August 6, JWST deployed its powerful near-infrared spectrograph NIR-SPEC, allowing astronomers to analyze the composition of the coma, the cloud of gas and dust surrounding the comet's nucleus. What the telescope found was nothing short of extraordinary. The spectra revealed a coma overwhelmingly dominated by carbon dioxide, with a ratio of CO2 to water unlike anything previously recorded in any known comet from our solar system. Typically, water vapor is the primary volatile released from comets as they warm up near the Sun, accompanied by smaller amounts of carbon dioxide or carbon monoxide. But 3I/Atlas displayed distinct and incredibly strong emissions at 4.3 microns corresponding to CO2, while water, which normally appears prominently at 2.7 microns, showed up only faintly. There were also detections of carbon monoxide at 4.7 microns, but again, not in the proportions expected. This unprecedented chemical signature suggests that the comet formed in a cold, distant environment in a star system very different from our own, where carbon dioxide froze abundantly and water might have been less available, or locked away beneath layers that have not yet sublimated. To further complement JWST's findings, NASA's SphereX observatory began collecting data from August 7th through August 15th. SphereX specializes in mapping the sky in infrared wavelengths, allowing it to study not only composition, but also dust properties and the structural nature of astronomical objects. The observations from SphereX revealed something surprising: a strong point source signature. In simpler terms, this means the telescope detected something compact and sharply defined, without the extended spread typically produced by dust clouds surrounding an active comet. This lack of extended structure introduced a significant layer of ambiguity regarding the size and nature of the nucleus itself. In normal circumstances, comets with active outgassing develop noticeable halos and tails composed of dust and sublimating gases. But 3I/Atlas appeared oddly restrained in this regard, as though its nucleus was either unusually cohesive, unusually reflective, or perhaps behaving in a way that does not match typical cometary physics. The data opened the possibility that the nucleus might be smaller or more condensed than earlier estimates suggested, or alternatively, that the comet's outer layers were composed of unusual materials that interacted with light in unexpected ways. During this period, the Hubble Space Telescope also contributed crucial visual data. Known for its unparalleled imaging capabilities, Hubble captured some of the sharpest and most detailed photographs of 3I/Atlas to date. These images revealed a dusty coma surrounding the object and the earliest hints of a developing tail. While SphereX's point source results raised questions about the extent of the surrounding dust, Hubble's visual confirmation of a coma helped reinforce the classification of 3I/Atlas as a comet rather than an asteroid or some unknown category of interstellar debris. Nonetheless, the dust cloud appeared somewhat irregular and inconsistent with typical cometary behavior. Scientists speculate that this could be due to the comet's long cosmic voyage, during which it was exposed to intense cosmic radiation and foreign interstellar environments that may have altered its surface chemistry and structural integrity over millions or even billions of years. Understanding the size of 3I/Atlas has proven to be one of the most challenging aspects of the investigation. Early measurements from Hubble suggested that the nucleus could be anywhere from 0.2 miles to 3.5 miles in diameter, relatively small when compared to other comets. However, subsequent observations began pointing toward a much larger estimate. Later data indicated that the nucleus might actually measure between 6.2 and 12.4 miles across, which would make it the largest interstellar object ever detected. One reason for this dramatic shift in size estimation is the uncertain nature of its activity level. Cometary brightness often depends heavily on how much gas and dust they release, but if 3I/Atlas is behaving in an unconventional way, either releasing fewer visible volatiles or releasing unusual materials, its apparent size could easily be misinterpreted. Further evidence supporting the possibility of a larger nucleus came from pre-discovery data gathered by the Rubin Observatory. Observations revealed that between late June and early July, the apparent diameter of 3I/Atlas expanded by nearly 3,700 miles, a staggering increase that occurred within less than 2 weeks. While such rapid changes might seem shocking, scientists explain that this growth is consistent with comets as they warm and approach the sun, causing volatile materials trapped beneath their surfaces to sublimate and expand into space. Still, even with this explanation, the rate and magnitude of expansion observed in 3I/Atlas stands out as unusually dramatic, suggesting either a highly volatile-rich composition or structural properties that deviate from the norm. All these combined observations point toward one unavoidable conclusion. 3I/Atlas is unlike any comet previously documented. Its chemical composition is bizarre, its physical behavior is unpredictable, its size remains uncertain, and its structural activity continues to evolve in ways that force astronomers to continuously revise their models. What makes this interstellar visitor even more fascinating is the fact that it was shaped in an entirely different planetary system, forged in cosmic conditions we can only imagine. Every molecule and dust grain it carries offers a rare glimpse into the chemistry of distant stars and planets. Researchers believe that by studying 3I/Atlas in detail, they may uncover clues about the variety of planetary systems that exist throughout the galaxy, and perhaps even learn more about the early building blocks of life. As the comet continues its journey through our solar system, each new observation contributes another piece to a puzzle that grows both more complicated and more exciting. Telescopes around the world and in space are expected to keep tracking 3I/Atlas for as long as possible before it eventually exits our neighborhood forever. For now, the scientific community remains captivated by its enigmatic behavior, recognizing that this rare encounter offers an opportunity that may not come again for many decades. The mysteries surrounding 3I/Atlas are far from solved. But what is clear is that this alien traveler has already expanded our understanding of the universe and challenged our expectations of what interstellar objects can be.